T of alpha over 2 and degrees of freedom. So df stands for degrees of freedom. I think I may have talked about that when we looked at the chart in chapter 5, but let's go over it again. Degree of freedom is a calculation based upon sample size, depending on the type of data you're using. And it's a little adjustment factor that compensates for the sort of data you're looking at, which allows us to use one chart in the back of the book, or one calculation if you're using software. So it turns out for this problem, when you're dealing with single variables, the degrees of freedom is always n minus 1, one less than sample size. Alright, so I want to be more specific for this problem. Alpha over 2 is 0.05 divided by 2, and the degrees of freedom would be 11 minus 1. So I need a t-score based upon a probability of 0.025 and 10 degrees of freedom. That's our t-score. So what in the world is that? Well, let's go look it up in the book. It's on page, I think, 650. So try to find that in your book. Okay, page 650. And I'm going to go down to 10 degrees of freedom. So the 10th line down, left-hand column says degrees of freedom, 10 degrees of freedom. And I'm going to go over to under the where it says probability of 0.025. 0.025. So 10 degrees of freedom, probability of 0.025, and the number in the chart reads 2.23. 2.23. All right, now what's special about 2.23 in this instance? Well, 2.23 is 2.23 standard deviations. In other words, for this kind of data, it's a very small sample, I'm using the student's t-distribution, the middle 95% is 2.23 standard deviations away from the mean, either way. Now you might recall the empirical rule. The empirical rule said that 95% of the data falls between -2 and +2 standard deviations. So empirical rule says it's about 2 standard deviations. For this sample, we're saying, well, it's really not 2, it's 2.23 is more accurate. And that's because we're using a sample standard deviation. We're using the small sample. This is what the student's t-distribution is designed to handle. So to be more precise, we need to use 2.23 standard deviations in our calculations. So in essence, I'm going to take the mean and I'm going to go forward and backwards 2.23 standard deviations, except I'm using the standard error of the mean, because this is not a single observation, it's a sample observation, sample mean observation. We use standard error of the mean. So I need to do a little racing, and I'll write down the formula that we use to calculate this problem. So give me a moment. I've written a formula on the board, and it reads this. Mu belongs to the interval x bar minus t-score based upon alpha over 2 and degrees of freedom times s divided by square root of n, comma, x bar plus t based upon alpha over 2 probability degrees of freedom times s over square root of n. Now you'll notice that this part and this part are identical, and so the confidence interval is x bar minus the margin of error and x bar plus the margin of error. So this whole mess here I'm going to call margin of error. Now this is in your book, but it's in a little bit different form. Same formula. If you look at the top of page 250, In fact, turn backward a page, please. Bottom of page 249. Bottom of page 249 says confidence interval for a population mean. And that's what we're doing here. We're finding confidence interval to estimate a population mean. And then when you go to the top of page 250, it gives their formula. And it reads, they have x bar minus t star s over square root of n, and then x bar plus t star s over square root of n. And I hope you don't find this too aggravating. I use t and t star the opposite of the way our textbook does. To me, this makes more sense because this is the t-score based upon these input values. So it's a function. And later, when we calculate a t-score, I'll use t-star. So the book uses an opposite notation for me between t and t with an asterisk after it. Okay. Well, sorry. Please get used to it. To me, this just makes a lot more sense. So anyway, that's the where you would find the formula in the book, and this is how I like to write it. So since I'm going to keep writing them this way, you probably want to just get used to the way I'm doing it. Keep your own list of key formulas that you would need for a test or homework. Well, let's plug some numbers in and make some sense of this. So now let me see, x bar was 77.2. We looked up this number. I erased it off the board. That's why I was hemming and hawing there. We looked up this number. It was the t-score based upon 0.025 and 10 degrees of freedom, because degrees of freedom was 1 less than sample size, 11 minus 1, times the standard deviation, 13.3, divided by the square root of sample size. And then we have 77.2 plus the same stuff. Alright, I don't have a lot of patience for recopying this calculation, so I tend to just put plus same stuff or stuff. Alright, so a little more specifically, this is 77.2 minus 2.23 was the number we looked up. 2.23 times, I'll do it in parentheses, 13.3 divided by square root of 11. And then 77.2, let me fix this, 77.2 plus the 2.23 times 13.3 over the square root of 11. So there's a calculation with all the numbers plugged in. And it may be a little hard to grasp at the moment, but think about this. This is the number of standard deviations times the standard error of the mean. And we're adding and subtracting it from the sample mean to create this interval of numbers. So let's calculate that. Now I need to make some room here. So I'm going to erase all this right here. Grab my calculator.